So today we are just going to finish our recapping and maybe take an example or maybe take questions from you. So within that pellet there is diffusion and reaction that takes place. Okay, as the diffusion and reaction takes place, we can possibly have a concentration gradient within the pellet. For example, if the diffusion rate is slow or the rate of reaction is very high, then there will be a concentration gradient within the pellet. Because of this concentration gradient, entire pellet is not effectively utilized. When is a pellet effectively utilized? When the concentration throughout the pellet is equal to the bulk concentration. That is when the pellet is effectively utilized or eta equal to 1. When it is not the case, then the eta will be less than 1, or in exothermic cases eta can also be greater than 1. Okay. So, these are the cases that that you would see. So, phi is the ratio of reaction rate and or an indication of reaction rate to internal diffusion. Or phi square is that, okay, which is going to be for 0 order okay, it is going to be K divided by d by r square. Okay. So, phi is going to be r square root of K by d. D effective. Okay. So, this is the definition of phi that is used for not 0 order, sorry, first order reaction. This is the definition. Okay. So, if for a spherical pellet no 0 order, it won't be the same thing because K will be moles per meter square per second. Okay, so it's K by C. I'll come to what will be the cases for 0 order and so on. Okay, so eta is going to be equal to 3 by phi okay. So this is what for a spherical pellet. Again, I am not sure if I made a mistake or not. This one should be 1 by phi. That is definitely right because otherwise you will get eta values as negative. Yeah, hopefully, I mean just check your textbooks for the correct expressions. Okay, it's possible that there's a mistake over here. Okay, this is the case for spherical pellet. Okay, for slab, tan h phi divided by phi, sorry. Okay, so this is for the slab. Okay, now if we were to plot eta versus phi on a log scale, okay, what we are going to get is we are going to get this for slab, this for a sphere. Okay, so we are going to get different things for slab and sphere, obviously, because your expressions are different. Okay, what people found out is that if you make a small change, and this is what this slide shows. Okay, this slide shows that for slab, for cylinder and for sphere, your expressions are different. So, here I switched them. Okay. So, your expressions are different for these three cases. Okay. So, this is what this particular figure says, but what Aris and co-workers in 1970s realized that if you make a small change in the definition of phi, all of those lines will fall on one and the same line. Okay. So, what was the small change in the definition that they did? This was the definition that they used. Okay. So, this would be applicable for any nth order reaction, okay, and any dimension, any type of catalyst pellet. Okay. Is this accurate? No, it is approximate. Okay. But the beauty of this is that for any power law kinetics or any reasonably arbitrary size or reasonably arbitrary shape of a pellet, this will still be applicable. Okay. If you have a very fractal pellet, or if the pellet is 3D printed to have funky shapes, yes, this is not going to be applicable. But generally the pellets that you get synthesized, whether it's say orthorhombic, whether it is say I don't know whether needle like will also be reduced to this or not, but any reasonable size pellets can, I think even needles will follow this. Okay, will follow this particular expression. So, what if this is a sphere? In the case of sphere, phi is going to be volume is 4 by 3 pi r cube, area is 4 pi r square. So, therefore, volume of pellet divided by area of pellet is r by 3. Okay. Square root of 2 by 2, which gets cancelled, k Ca raised to 0. So, this gets cancelled, divided by EFF. Okay. This is the phi. If you use this phi, then our eta is equal to tan h phi about divided by phi. Okay. What happens in case of first order reaction in a slab? First order reaction in a slab, V by A is nothing but L. The stuff in the brackets is K divided by D. So, our capital phi is exactly equal to small phi, and the eta expression is exactly equal to the eta expression that was derived. Okay. So, for a slab using generalized Thiele modulus or the original Thiele modulus, you are going to get the exact same result. Okay. For a sphere using the generalized Thiele modulus and using the regular Thiele modulus, you are going to get slightly different result. The generalized Thiele modulus result you get is this line. The Thiele modulus using sphere, the regular Thiele modulus, the small phi Thiele modulus is this line. Are these two lines same? They are not. Okay, but they are reasonable approximations of each other. Okay. So, what I said was that in your problem statement for your exam, we would explicitly say whether it's going to be capital phi or small phi. Okay. If it is not specified whether you have to use capital phi or small phi, you are free to use whichever you want. If I was in your place, I would be using capital phi. That's all I said. Yes, you'll underestimate using capital phi. Yes. Yes. So, one of the problems initially that you guys will face, whether you start working on an experimental research, whether you go to industry, whether you go for research, is the numbers that you are said that we say over here and the numbers that you get in from actual real world, they are not the same. You will never get, they say, exact same number anytime. You repeat the experiment 5 times. If your techniques are very sensitive and very accurate, at one time you might get 15.1, another time you can get 15.2, third time you will get 15.0, fourth time you will get 15.1. So, it will be very closely clustered around 15.1. Typically, your errors are of the order of 5% at least. Okay. So, the error that this is going to create is going to be less than the error in estimating your K. Okay. So, for example, if you were to fit your activation energy type the Arrhenius plot, you will basically get data points like this. Okay. Okay. The best line perhaps is a line like this, but the data points are never like this. Experimental data points are with error bars. What this means is the data that is plotted is the average value, but if you run the experiments 3 times or 5 times, you have never got the exact same value, you have got the values around it. So, anyway your experimental error is of the order of 5%, the error in using capital phi versus small phi is less than that. Okay. So, yeah, I mean that is the practical implication of it. So, for again as I said, we use Weiss-Prater criteria for our experimental evaluations. For simulations, we usually do not use phi, we use basically heterogeneous models. But if I were to use phi, I will use capital Phi because the definition is more general and very seldom we have spherical pellets. Okay. So, it's more appropriate to anyway use this for a lot of practical cases that we see. Okay. So, let's take a case. I think this is similar to the one you have solved already. This is from I think last year's problem sheet. Okay. So, the question basically is partial pressure of A in the bulk not B or A. Okay. Question number 1 was Phi H or gamma. So, what will be these values? Okay. And therefore, what is going to be effectiveness factor. Okay. So, again I mean I think you have We have solved this before. We have taken up example during the tutorial as well. We have done an example for regime 1, regime 2 and regime 4 systems, and again this follows on the same lines. This is regime 3 or between regime 2 and 3. Okay. So, for the and skipping the overall derivation, if the derivation is done if the reaction is first order in A, okay, and 0 order in B, okay. When is it in 0 order in B? Let us say the so in this particular example, right, the concentration of A is 0.001 bar, okay, and therefore the concentration of A at the interface in the liquid is going to be 0.001 multiplied by 40, okay. So, it is going to be basically 0.04 moles per centimeter cube, right, which is basically millimolar concentrations. The concentration of A is in millimolar terms. If PAI was equal to 1 bar, then concentration of A would have been 0.04 molar. Okay, that also is reasonably low compared to the bulk liquid. Okay, so what happens? Let's say the reaction is A plus B giving product. Okay, let's say you have 1 molar solution of B and you have 0.04 molar concentration of A. Okay, what's the maximum amount of B that will get consumed? Only 0.04, just by stoichiometry, not by reaction rate, not by this. So, you cannot exceed 100% conversion. 100% conversion of A will mean 0.04 moles of A have been consumed. 100% conversion of B will therefore mean stoichiometric coefficient nu B by nu A multiplied by concentration of A will be the one that is consumed. Okay, so maybe 0.04 will be consumed, maybe 0.02 will be consumed, maybe 0.08 might be consumed, but that's still significantly lower than the bulk concentration. Okay, so even irrespective of what regime this particular system is in, your concentration of B is not really changing. Okay, so your reaction intrinsically, the reaction might be first order, half order, third order, 75th order in B, doesn't really matter because the concentration of B is not changing. So, if you were to do experiments, it will seem as if it's independent of B. Why does it seem it is independent of B? Because B concentration is not changing. Okay, not actually because it's independent of B, because the concentration of B is not changing. That's why it will look as if it is independent of B. Okay, so that is what pseudo first order means. It's not really first order, but for all practical purposes, we can take it first order simply because the amount of A that is present is significantly lesser than the amount of B in the liquid phase where the reaction is taking place. Okay. Now, what is the value of delta? We use, very simple idea. Delta is K is D by delta, and therefore you can calculate delta. Okay, so you end up calculating delta. You put your delta in this particular expression. Okay, here you are not given. So this is basically, we encountered a situation like this. I told you yesterday, right? So CO2 is present over here, H2O is present over here. CO2 dissolves in water, okay, and then it would react with water to form hydrates. Okay, so although one molecule of CO2 will react with 6 molecules of water to form hydrate, concentration of water is very high, right? It's 1000 gram per liter, 1000 divided by 18, that many molar, right? Water cannot diffuse in itself. I mean there's no concept of diffusion of water in itself. So therefore, water concentration is always going to remain flat in uh, in the liquid phase. Okay. So CO2 now gets dissolved. Okay, and let us say, let us idealize this interface. Okay, the interface is like this. We will have the film. Okay, in the film, CO2 is uh, getting diffused as well as it is reacting. This reaction is taking place in the film as well as in the bulk. Okay, so that is the situation that happens over there. What's the thickness of the film? Thickness of the film is nothing but diffusivity divided by the KL. How do we get KL? We get KL experimentally. Okay, so that is the first part done. Thereafter, you substitute the values of KL into this particular delta into this particular expression, you will get the value of phi. Okay, so delta in this particular, so your from these two guys, CAI is going to be 0.04 moles per centimeter cube. Okay, from these two guys, our delta is going to be 6 into 10 to the 0.1 cm. Okay, so our Thiele modulus is going to be 0.1 square root of, so that's by 6. Okay, so this will give one value of phi, the next one will give another value of phi, and so on and so forth. Okay, and you can get the various values of phi. Okay, and then you can substitute them. You can substitute them in your eta. Okay, so with when you substitute this into the eta expression, you will be able to get your desired results. So that is how you would solve an mass transfer with reaction gas liquid case. Okay, what if it is regime 1, regime 2 or regime 4? It's a lot more straightforward if it is one of those regimes. It's when it is between 2 and 3, that's when it's a little bit more complex. Okay, and all of those problems we have tackled as a part of tutorial and as a part of the assignment. Okay, most of the derivations that were there in the assignment, the details are not there, but you know, skipping the steps, the derivation are there in your Froment and Bischoff. Okay, so, I think even the reversible reactions and other, I don't know what assignment problems I had given you, but even the reversible reactions and all that, all the derivations are there. They have basically skipped steps, so you can go and look back into the textbook in order to revise the derivations if you need to. Okay, yeah. Yes, why is it there? Okay, so what is the definition of Sherwood number? Expression, fine. Yeah. What if L is not known? Okay, one way to do L when it is not known is something like this. is this applicable for Sherwood number? Where does the Sherwood number exist, or what diffusion is the Sherwood number trying to capture? Where? Diffusion where? Gas or liquid? See, this is the only challenging thing. I don't know why is it challenging. I thought it was straightforward. CO2 diffuses in the gas and reaches the interface. CO2 then diffuses in the liquid and reaches the bulk. Okay. What mass transfer does this Sherwood number talk about? It talks about a mass transfer in the gas phase. Oh no, this is Sherwood number in the liquid phase. Sorry, my mistake. Okay. So you have KL L divided by D. Okay. So one way to get the KL is an expression like this. This is when you have your when you have a situation like this, where you have bulk liquid, okay, and the interface is much smaller than the liquid, okay. But when you have cases like bubbles of gas going through the liquid, very large bubbles of gas going through the liquid, or a falling film type of situation, or you have droplets of liquid falling into gas, okay. In that case, what happens is that the entire liquid is going to be consumed. There is no real bulk over there. The entire liquid is going to be your film. Okay. When situation like this comes in, your L is defined as V by A. Okay. So that would be the one context. But again, I mean, I don't think any of the examples that I have given cover that. Okay. So that's so I'm not exactly sure where. So all the examples that I'm giving you are, or I don't know if this is the A you are talking about. I mean, you can't take an expression out of context and say what I don't really know that. Okay, so in this Sherwood number, yeah, I don't think you have to do a correction for area. Okay, over here you are doing correction for area per unit volume because you have K over here. If it 1 divided by KL plus H divided by Kg plus 1 divided by K dash. This will be the expression. Okay. Yeah. And we can have, right. So that's how this comes into picture. Your K is then defined in that way. Okay. So that's the reason why A comes over here. If you think about what we wrote in module 5A, right, or right. So this is how you'll end up writing. You divide throughout by K kg A bar, you are going to get 1 divided by 1 by K. Okay. This and this, they have exact same type of representation. Only difference is that in module 5 you had only one film, which was the gas film. In module 6 you have, in module 7 you have a gas film and the liquid film. So this takes care of intrinsic reaction, this takes care of gas film, and then there is one more for liquid film. Okay. When does this happen? This happens when no reaction is taking place in either the gas or the liquid film. Okay. It is not like no reaction is taking place, all of the reaction is taking place in the bulk. That is when this situation happens. So, it's in gas liquid systems compared to gas solid systems. There is only one additional thing that you need to do, figure out, not exactly figure out, it will be given to you, what regime this particular system operates in. Okay. Regime 1 and 4 are fairly straightforward, regime 2 is semi straightforward. Okay. It is only regime 3 that is a little less straightforward. Regime 1 is equal and 2 are equivalent to your external mass transfer limitation. Regime 3 is equivalent to your external as well as internal mass transfer limitation of module 5D of module 5. Okay. Equivalent between regime 4 and gas solid reactions is not there. Okay, there is no real equivalence between them. Okay. Well, there is, but that is where the reaction takes place only on the solid surface, but then there is no internal diffusion at all. So, it is not exactly the same. So, otherwise regime 1 is equivalent to external mass transfer limitation, regime 2 is equivalent to external mass transfer limitation and the reaction is taking place in the bulk liquid. Regime 3 is equivalent to external and internal mass transfer limitation. Regime 4 is unique to gas liquid systems. So, that is the relationship between module 5 and module 7. Okay. Again, I mean, for when you are analyzing the systems, you do not really need to look at those equivalents, but if that thinking about those equivalents helps you in solving problems, yeah, so be it. Okay. For while doing ideal reactors, we had recapped how to solve ODEs. Okay. Yesterday I talked about also how to solve algebraic equation when you have quadratic, right, minus b plus or minus b square by 4ac. Okay. Yeah, so just kind of familiarize yourself with that. Again, high school math was about how to get the minimum or maximum. Okay. So, find the temperature at which selectivity is maximum. S is in the numerator, T temperature is in the denominator. So, D of selectivity divided by D of temperature, that is what this is. Okay. Overall balance equations, look at these two slides. Okay. Your dVck by dt equal to this. Okay. If it is well mixed steady state, your green term is 0. If it is batch reactor, your black terms are 0. V rho Cp and all those are the terms that will be given to you. Yeah, in what form you want to solve these equations, it's really up to you whether you want to keep it in concentration form, whether you want to do it in conversion form, or whether you want to do it in extent of reaction form. Okay. We have often when we are solving these type of expressions, we use a convenient form that allows us to convert multiple equations into a single equation. Okay. So, we have either converted everything into conversion form, that means we have expressed everything in terms of XA, or we have converted everything in terms of CA and CA in, or CA and CA 0. Okay. Those two, and those two are equivalent. Why? Because XA has one-to-one relationship with CA. So, you can use either of those approaches. Okay. Your undergraduate textbooks use XA in order to solve. So, if you are comfortable with that, you can continue with that. Okay. For exothermic adiabatic case, not exothermic, for adiabatic case, your T is T in plus delta T adiabatic multiplied by conversion. What is the delta T adiabatic? It is the amount of heat released if complete conversion is happening, divided by rho Cp or Q rho Cp or V rho Cp, as the cases might be. And then we have done this particular problem. dP by dz, it's not kind of, I mean, you can get dP by dz in to directly solve that, you can get, but to use dP by dz and look at pressure drop and then solve a PFR balance equation, you can't do it by hand. Okay, so you can remember the concept or whatever, understand the concept, but yeah, numerical problems, those require some kind of a software to solve. Yeah, so that's, and this is how we integrate. The integration rule, trapezoidal rule, again you don't need to remember the trapezoidal rule. If I ask you a problem on trapezoidal rule, I will give you the formula, okay, but remember how that formula was used. So the idea is that I hope all of you have a clear picture of what we did in the last 13 and a half weeks. Okay, all right, okay, thank you very much.